project developing an approach to do autonomy for the rover on the moon. And he has been using, started to use the methodology I just showed you in Obsidian. All right. So Nicolas, take away.
Okay, so thank you for the introduction. So I'll basically describe some early work on this prototype of a long-range rover technology. I'll give you some context about what that prototype is. And in particular, my focus will be to explain what makes defining writing ConOps for autonomous systems particularly difficult, and how could we actually address some of its pain points with a ConOps perspective backed by this Sierra methodology that Maggot mentioned. Right, so the context. Here I show you 3 generations of autonomous rovers. You see on the right here, this is the Mars 20 engineering model. So it's the Perseverance rover that is currently on Mars up there. On the left, far left, my mouse is, it's over there. It's a little bit difficult to see. This one is there were 2 Cadre rovers in the Mars yard that day. Cadre is some very small rovers that demonstrate distributed planning and scheduling to be deployed next year in the IM-3 launch. And then in the middle, this is our puppy, TLR, or we call it Ernest. If you're interested, I'll explain you why it's called Ernest. And so this is the main difference between those 3 is that the one in the middle, Ernest,
catch one. Oh, I thought you were trying
to. Is basically the first time where we use the JPL autonomous technology for planning and scheduling. Somebody has an open mic. If you can please close. It's the first time that we packaged JPL's planning and scheduling technology as a component, library component, and make a clean separation between that technology versus how it is used and tailored for a particular application, in this case, this TLR rover. Whereas on the Mars 2020 onboard planner to the right, or the Cadre rover to the left, the reuse of that technology was at the code level. And so there's a lot of mix between that off-the-shelf technology and project-specific code that makes separating the 2 very difficult. And so even though all 3 of them have some conceptual similarities in the way they operate, we can't really compare them in a very precise way, which was a big no-no for me. So I kind of put my foot down and made a cleaner reuse of the technology. This photo is a long duration exposure of actually this rover driving at night. And this is another first in that all the rovers that we've developed at JPL and that we've flown drive during the day, whereas this TLR rover is designed to actually drive day and night without actually having to change camera settings, apertures, and things like this, which presents its own kind of challenges, but it's a pretty big deal. So now I'm going to describe what makes actually defining concepts operations for this kind of rovers hard, and there's 3 kinds of challenges. The first one is procedural versus goal-oriented behaviors. So in a traditional space mission system, right, we operate these things with sequences of some kind, maybe sequences with branches or anything else. But the main thing is it's predictable behavior. That predictability simplifies V&V because you know what to expect. And we can actually delay the development of ConOps until fairly late when all of the details of those behaviors become clear. Whereas if you have now an autonomous system, particularly if you have a lot of autonomy, well, it's a different thing because now it operates with some kind of intent on board. That means it's going to make decisions. It's less predictable. In our case, that intent is encoded using our JPL mission executive technology as a task network. It kind of looks like an activity diagram or BPMN process. The main difference is that at runtime, that particular activity diagram or BPMN process can actually be edited. Like we can add things, we can remove things, we can swap things around. So that makes basically predicting the behavior much more difficult. On top of that, that intent is specified using logical constraints, which is a paradigm that many system engineers who are used to traditional ConOps are not used to think in terms of. So how do we specify an intent-focused ConOps, which is still a question we're trying to answer, but I have some clues about the answer to that. The second one is actually the hierarchical nature of autonomous systems. In our rover case, we actually have 4 layers of autonomy, which is kind of like pointed with the red arrows. At the bottom layer, there's basically this thing called local motion control. It's basically very short range navigation. There's an intermediate level, we call it local motion planning, which is basically around the visible horizon using stereo vision about finding a path. And it then sends intermediate goals to the lower level locomotion planner. And then we have global motion planning, which is from one waypoint to another, where now it's calculating a long range path. And then above that is now the system level autonomy that is now responsible for managing resources. Are we driving? Are we communicating? Are we doing something else? And so on. The part that makes this difficult for ConOps in this context here where we're talking about a research prototype is that we have actually domain specific experts across all 4 levels. They're not the same people. They work fraction time. It's very difficult to find all of them in the same room at the same time. So describing exactly how this whole thing is going to work together is tricky. So Elisa was talking about problems with people having different vocabularies, terminology. That same thing applies, right? A low-level robotics control talks about paths differently than a robotics navigation planner, which talks about it differently than an autonomous engineer, right? Analyzing those cross-level interactions is actually hard in part because we're not talking about a view of the system that is reflected in architecture diagrams like this one. It doesn't quite fit. So part of the challenge is that the views that we need for contextualizing ConOps sometimes need to actually be elaborated by querying the relevant components. So again, this is the kind of thing where Maged was talking about having views that could be actually defined by perhaps queries that could be particularly powerful. The third challenge, and perhaps the biggest one, is observability. And right now, we've found a lot of problems because of the interactions across the 4 layers that I've mentioned. And right now, it takes sometimes a team of literally experts and whatnot to discuss and figure out what happened when a problem occurred. And this leads to the question about, do we have the right ConOps? We tried all kinds of techniques, UML, sketches, PowerPoint slides, Excel spreadsheets, textual narratives. But in fact, looking back over our experience over about a year and a half, I realized in many cases we don't have the right ConOps Why? For two reasons. Sometimes a ConOps written by, say, an autonomy system engineer doesn't really speak to a locomotion low-level engineer and vice versa, so terminology differences. The other aspects is we have this middle layers, as I mentioned, right, that straddle different places in the architecture, and sometimes you have stuff happens in the middle. And so it's difficult to account for all of these indirect interactions. And then the big second factor is over time, I saw ConOps rot. Right? You spend a fair amount of time writing ConOps, and I see Marcus like nodding, right? And I was like, yeah, this is a great ConOps, and explain it to the team, review it. Everybody says, yeah, good, good, good. And then stuff changes, right? The implementation changed. We decide to change the venue. We are testing in the Mars yard versus the desert, and blah, blah, blah. Now the ConOps is obsolete. And it takes more work to actually update it. And so the fact that it's painful to update ConOps, again, UML sketches, PowerPoints, spreadsheets, whatever you name it, to me means it's the wrong paradigm because it's not sufficiently agile for people to actually maintain them, just like we maintain code and other things. And part of the reason is observability. Observability is essential to define good test scenarios, right? If we say, well, we expect the rover to do A, B, and C, well, how do you tell if it has done A or D or B or E or whatever, as opposed to what you want? And ConOps without observability then prevent defining good scenarios. It's almost like a vicious circle. And so how can we actually address these problems? So kind of like back to the square root. ConOps should specify goals that we can test and observable states that we can verify if in fact it happened the way we expect to. So specifying goals in a traditional approach, think again, procedural, well, there's no goals. There's like an imperative things, do A, B, C. So the goals are implicit, right? The intent is not explicitly written. Why did you choose this sequence as opposed to something else? Why did the chicken cross the road? I don't know. So the intent is indirectly conveyed, which contributes to creating confusion, communication problems, specification rot. In a declarative approach, you specify goals as logical properties. Again, properties about observable state. If we don't have observable state, we can specify a goal about we want those states of affairs to be like this after we've done a certain number of things. So observing states, when in a traditional approach, well, we specify some event sequences that might provide some indication of progress, right? You expect to see your drive commands, you expect to see the motors moving somehow, and eventually you reach something, but it's not necessarily very clear. In a declarative approach, you have to start asking questions about what it is that you need to observe to verify, in an unambiguous way, progress toward the goal, because you want to know, are we getting stuck or are we actually doing something towards the goal? And when do we tell that we're done? The second part is, where are those observations going to come from? Maybe it's multiple levels. I can tell you that, for example, driving as a goal and defining a ConOps as a goal on our rover, I wrote this using temporal logic formulas. I don't know if you guys are familiar with temporal logic properties. So the idea of temporal logic is to describe what happens in time with operators to say, I need to observe, say, this particular command. And then you have some operators that say, eventually, I need to see the following within maybe some time. Or I should never see drive to this followed by drive to that. Before I should see drive to this, then some stop, then drive to something else. So it's a way to effectively be a bit more relaxed in describing what you want to observe in time, not by being explicitly prescriptive, but effectively a bit more loose. And in formal methods, there's a big community about runtime verification that uses temporal logic to actually verify what we call safety properties, meaning the system should be robust against things that may go wrong, and liveness properties, meaning that the system should eventually do something good, even though there may be a bunch of impediments. And some of the biggest advocates for using temporal logic formalisms are actually chip-making companies. Intel is perhaps the most famous example, where I think it was like, I don't know, Pentium 3 or 4, I don't remember, there was like this arithmetic bug that cost like Intel millions of billions of dollars. And they started to actually wonder, well, how can we avoid those kinds of bugs at design time instead of finding out later? And part of the answer was, using these kinds of formal methods based on temporal logics. The point here is that temporal logics and ConOps are really made for each other, I believe. Unfortunately, in practice, we don't do this much very well. So in our case, in applying this HERA methodology that Magged roughly described, and unfortunately, I don't have more like concrete examples besides where we're going with this, is that we're basically are trying to capture the components. The point of this chart is that we're actually not capturing all of the components in the architecture, only the subset that is relevant for autonomy. That means that we actually have to be more proactive in engaging with the architects that make those kinds of PowerPoint doodles, or sometimes call them boxology, because they don't mean anything except it's a stale PowerPoint chart, to make some architecture diagrams that remain in sync so that we don't have basically inconsistent diagrams all over the place, which is the point here. The second part is we have to describe activities. So here is, we did some testing of our rover in the desert in Ocosito Wells, which is in the south of California, close to the Mexican border. And for example, we had to describe, activities like clearing and loading a task network. We have some flexible scheduling. We want to drive until the waypoint is reached. But there's a bunch of interruptions that can happen and did happen. Like, for example, some of them that are intentional is the first sub-bullet. High priority communication for us had a higher priority than driving. So if it turns out that there was a high priority file that came into the system, we had to stop driving to communicate when there was an orbiter visible, in the sky. But there's some other interruptions, like the second sub-bullet. For example, if we press the emergency stop button, that's a red thing on my pocket, it's a Wi-Fi button that is in the range. But if it turns out that because the Wi-Fi base station was inside the rover, which is metal, so it's in a Faraday cage, we had to be very close to the rover. Otherwise, if we were out of range, the Wi-Fi receptor on the rover would actually stop because we're out of range. So this is an example where, why did the chicken cross the road? Well, why did the rover stop? Well, there's all kinds of reasons. And unless you have good observability, it could actually be a problem in verifying that you have econops that happen for the right reasons. Then mobility autonomy. There's all kinds of things that we turned out to have to do. Some were basically found later, like resetting the EtherCAT hardware, which turned out to actually fail far more often than we would like to. The point of all of this was that for this rover, we made a test back in April last month, 14, 16. We drove almost like 2/3 of that route, which was 18 kilometers. This on the right is a picture of a shift. We drove day and night in shifts of about 8 hours each. So it was a quite useful experience. And what we actually realized, or what I realized, is that even though this is a research prototype, even though this is kind of like, in some ways, early mission type work, there's some aspects like driving a prototype in the desert that looks like phase C, D type work. So you can't pinpoint ConOps as early or late phase. It's really, across the board. And the main thing is we basically need observability and goal-based verification to make it work. Otherwise, we don't know if a particular scenario succeeded for the right reasons or for just happenstance, which is the worst. And so we're on the progress to do all of this with the Sierra method. I don't have much to say beyond the fact that we need small vocabularies, because in the past, we had tried to use large vocabularies like XML. It turns out to be a big cognitive barrier for most engineers. So having a small vocabulary like Maged was showing will facilitate conveying how we're codifying the information from this markdown interface. The markdown interface is a great way to reduce the barrier of entry. The rigorous foundation there is important in that going from markdown to ML, well, of course, we want to do the analysis and so on. But the other aspect is from OML to markdown, in that there's a rich amount of information from scenario logs that I want to extract and push as OML data, almost like as if to say, the rover did this particular thing in this particular test, turn that into a scenario as if someone had written that, and compare whether that scenario of what the rover did matches the intent specified by a system engineer. That way, we have a richer form of verification and hopefully automate the process of extraction and verification. And so I believe that there's a paradigm of autonomy ConOps that does this kind of verification and validation on the basis of observations and goal verification.
So Nick, there is a question in the chat. Would you show a sample of the temporal logic statements you're asserting?
Oh, really? You want to see the code? Well, I just happen to have it. So this is basically so it's written in Scala, one of my favorite languages. And so here you see, let me start here. So the way we do driving is that always it's basically a for-all operator in temporal logic. And this case basically says, if we see an event called a dispatch request at some time, at some clock for a task and a template, where the template says this is some kind of a drive, because we have different kinds of drive machineries, then we want to look for then we want to look for some possibilities. If we were to see a request for the same task, because you see this is in the, is in the same place as that, that would be an error. Whereas if we see navigation, then that's progress. That means that now we expect to see other things. One of the things that we're doing with these temporal logic properties is that we're basically, you see this statement here, high level. We're using hierarchical, actually, temporal logic properties to compute some statistical summaries about the events that matched during a temporal logic formula. So we start doing something, we see several events, think of it like the stack trace from this kind of event to that kind of event and to this kind of event. So all of those events would be part of the trace in the temporal logic. And based on the trace, then we can actually compute a useful summary about what happened. And those summaries turned out to be very useful to compare, say, for performance analysis, the influence of various parameters on different events that span formulas.
Can I quickly comment? Adding the temporal logic vocabulary to Sierra is work that it's our next step of development. So
Right. Yeah.
Nick has already thought this through down at the code level. We need to abstract that up into vocabulary.
Right, because not
capture
everybody
it.
is love Scala. Yes.
So Nick, there is another question in chat. How do you compare scenario variance or detect subtle behavioral regressions when interfaces and implementations change?
Yeah. Okay. So this is a very good question. So the extraction actually so here I mentioned extraction from the scenario logs. But another big factor is that when I said, observability, right, you have to identify the states, the events that you want to observe to specify the ConOps. The flip side of it is it basically gives you the basis to say, if any of those events were to change in the implementation of a prototype, then you want to know about it. And so in a sense, you can use those specifications both to convey, well, we can express the ConOps in this form, but also effectively as a canary in the mine to recognize when any event mentioned in those observability criteria changes for whatever reason, and now therefore you have to revisit those ConOps. Yeah.
Can you hear me? Yeah.
We need to move the microphone closer to you.
Yeah, you are talking about sequential versus conceptual.
Yeah.
But
it's actually, yeah, I'm not sure about if it is conceptual, but it's really declarative modeling of ConOps.
okay, because we have to take care of the sequential part as well, right? Validations. Like you have to see whether
yes, but is it okay? So how do you accommodate basically sequential behavior in this paradigm? Well, it's simple. With temporal logic formulas, you can basically say, I need to observe A followed by B, followed by C, followed by D. So in other words, with temporal logic, it subsumes writing sequential behaviors. It subsumes writing sequences with if then else and conditions and branching. It's just a different perspective, a different way of looking at behavior, right? The difference is that with sequences, well, the only thing you can do is you can execute them. Sequences don't tell you don't give you enough precision to act as a detector to say, did this sequence happen? Right? Typically, we have sequence engine to execute, but not to tell you, did this happen? Whereas temporal logic formulas with monitoring techniques, you can actually use them, and I use them both as predicates. Do I match this? But you can also use them in a more imperative fashion to say, if I see A followed by B, then I want to inject a command to do something.
it's like back and forth.
Right.
Okay.
You can, it's.
Okay, thank you, Nick. Great talk. We will be moving to our next speaker, Lois Humphreys from Leonardo. Will be talking about their effort developing a system